Hello again. This is Math 2233 coming to you from the College of DuPage, and the title of this lecture is Special Vector and Scalar Fields, the Gradient, the Curl, and Divergence. As always, be an attentive learner as you watch this video. Recall that the gradient is defined as the gradient of a function f of x and y is the partial of f with respect to x in the I direction plus a partial of y with respect partial of f with respect to y in the j direction. Therefore, the gradient is really a vector field because it takes a point xy and maps it to a vector. So it's really a vector field on R2, and it's called the gradient vector field. Likewise, if f is a scalar function of three variables, that's lowercase f, its gradient is then a vector field on R3, given by this, partial of f with respect to x, I, partial of f with respect to y, j, and the partial of f with respect to z, k. So here's a problem for you to do. Find the gradient vector field of this function, f of xy equals x squared y minus y cubed, and plot the gradient field together with a contour map, and how are they related. This is a little bit of a review, but it is useful. You know what to do. Let's see how you did. All right, so when you calculate the gradient of this f, you should get 2xy in the I direction and x squared minus 3y squared in the j direction. And you could use technology, or you could have graphed this yourself. But here is a contour map. But then we've overlaid the gradient over it, and so that is the gradient vector field that we have. Now notice the gradient vectors are perpendicular level curves. We knew that from our previous learnings. But note also that the gradient vectors are long where the level curves are close together and are short where the curves are further apart. That also makes sense. That's because the length of the gradient vector is the value of the directional derivative of f, and closely spaced level curves indicate a steep graph. So this is the answer to this problem. A little bit of a review. A new definition. A vector field f is called a conservative vector field if it is the gradient of some scalar function. That is, there exists a lowercase f such that f, the vector field, is the gradient of lowercase f. In this situation, lowercase f is called a potential function for uppercase f. This, I know from experience, confuses some students because the roles of lowercase and uppercase f are somewhat reversed from what you did in Calc 1. So make careful note of this. Since we have a definition for this, you would expect that not all vector fields are conservative, but fields that do arise frequently in physics are conservative and has meaning that are important relative to the conservation laws of physics and engineering. And one example of this is the gravitational field, capital F, this one, down here, okay, which is equal to this, is conservative because if we take lowercase f to be this one, then the gradient of lowercase f equaling these is actually equal to uppercase f of x, y, z. And again, this gives you a chance to think about the notation. So this is conservative because there is a lowercase f that we can find such that the gradient of this guy is equal to this guy. And we'll have stronger theorems than this to have later. And we'll also go through an exercise where we actually construct the potential function, at least when we can. We're now turning our attention to a different topic that is called the curl. And this is only meaningful in three-dimensional space. So if capital F is equal to Pi plus Qj plus Rk is a vector field on R3, and the partial derivatives of all those coefficients all exist and have the right level of continuity, then the curl of F is the vector field on R3, defined by the curl of F is equal to the difference between these two partials in the I direction, the difference between these two partials in the J direction, and the difference between these two partials in the K direction. That's quite a mouthful, and you really aren't expected to memorize this definition. I'm going to show you a more computational, viable way to do this. But the curl is a vector, and these are the coefficients. Okay, so as an aid to our memory, so we don't have to remember that, we introduce a little bit of notation. And we're going to talk about the vector operator that is called del. And del is equal to I, and then we take the derivative with respect to x plus j. This is the derivative with respect to y, and this is k. That's the derivative with respect to z. Now you might think, oh, this is the gradient, but it's not, because the gradient is a vector that has components. First of all, that does operate on a function, but this has components. But you see here we're adding these components together, not just taking the partial derivatives. So this is something new, and this Greek letter is called del. And it has meaning when it operates on a scalar function. So this is del f. It's this, and it ends up being this. But notice that what we're doing is we're adding these partials in the I, j, and k direction. Now with this new notation, what I can do is I can take del cross with f, and I can, now I'm using the notation that we had before for the cross product, even though the notation is a little bit clumsy, because this really, like these are the I, j, and k vectors. These are the vector, the components of what we have in each of the I, j, and k directions for del. And then this is P, Q, and R. And this order does make a difference. But if we use the definition of the determinants that we've talked about before, and you can see what happens when you do here in the I direction, I'm going to cross out this column and this row. So I have the partial of y with respect to the partial of r with respect to y minus the partial of q with respect to z. Then I go minus, because it's in the j direction, cross out that row and that column. But here, because of the double negative signs, what happens, I get minus the partial of r with respect to x and plus the partial of z with respect to p. So when you do the minus signs, you get this. And then last but not least, here we don't have to worry about these signs, so this is the partial of x with respect to q minus the partial of p with respect to yk. So you see that del cross f is a wonderful way to remember the definition of the curl of f, and is a great way to compute it. So if capital F of x, y, z is this vector, find the curl of f. You know what to do. Let's see how you did. So the curl is this calculation. We go through and do it. You should pause and make sure you're getting this calculation right. But once I simplify down here, and there is some simplification involved, there's minus times minuses and things like that. When you combine it, you should get this answer. Now, recall that the gradient itself, we talked about that earlier in this lecture, of a function of 3 variables is a vector field on R3. So we can compute the curl of it. And so here's the following theorem that says the curl of a gradient vector field is 0. And you see here is the, so the gradient is a vector field, and so we can compute its curl. So the following curl says that the curl of a gradient vector field, but this is the gradient vector field, is 0. So if f is a function of 3 variables, then the curl of del f is equal to 0. You know what to do. Let's see how you did. So if f is a function of 3 variables that has continuous second partials, then this is true. Well, we're just going to do that. Now this is the del operator, so I get this as the vector on the bottom, but then I'm going to be taking the second partials here with that. And when I go through and take those, what happens is that whenever you're doing these calculations, this is the partial going with respect to yz, this is with respect to zy, so with the assumptions on continuity, that's 0. Similarly, the order of taking the partial derivatives doesn't matter, and so we get that this is equal to 0. So if f is a function that has continuous second partials, and this is Clairaut's theorem, then that was Clairaut's theorem before, that the order of the partials is the same, then the curl of del f is equal to 0. And this is the proof of that. Note, this is similar to that a cross a is equal to 0. And we've talked about that before. Now, since a conservative vector field is one for which capital F is equal to the gradient of lowercase f, we can rephrase the theorem that we just had to say, if f is conservative, then the curl of f is equal to 0. And this gives us a new way of verifying that a vector field is not conservative by taking the contrapositive of this statement. So here's an example. Show that the vector field capital F of xyz equal xz in the I direction, xyz in the j direction, and minus y squared in the k direction is not conservative. You know what to do. Let's see how you did. Okay, so you computed, and actually this is what we've computed before, but that's not identically 0, and so by the preceding example, it's not conservative. Now the converse of the theorem is not true, but if you have a nice enough f, where capital F is defined everywhere it is, and so here's the theorem. If capital F is a vector field defined on all of R3, and the component functions have continuous partial derivatives, and the curl of f is equal to 0, then it is a conservative vector field. Now this is a proof by construction, and so instead of doing this, what we're going to do is we're going to do an example. I'm going to ask you to do it. Show that this vector field is conservative, but then we're going to find the f. And this proof follows from the general construction like this. So find the lowercase f such that capital F is equal to del of f. So that's what we have going on, and you know what to do. Let's see how you did. So we compute the curl of f this way. Make sure you follow this calculation and you can get it, but it is equal to 0. You see, I'm liable on the test, on the final exam, to ask you to compute the curl of some vector field. So you need to know how to do this, but we do get that it is 0 in part A. But now what we need to do is we need to work through and we need to find the capital F. Okay, so what we do is we know that by differential functions that we studied earlier, that the derivative with respect to x is this one, and the derivative with respect to y is this one. And the derivative with respect to z is this one. So what we can do is we can integrate one of these, like the top one with respect to x, and we get this. Now this is a function now, it is a constant, but because we're integrating with respect, this is a constant of y and z. So what then we can do is we can differentiate this partial derivative of this with respect to z, and we get this kind of an expression. But then we compare this to the previous statement up here, and we find out that h prime of z has to equal to 0. Therefore, f is equal to this. But this is still a function of y, so the problem continues. And we can solve it that way. The reason for the name curl is that the curl vector is associated with rotations. And there are many actually connections, but one happens is that when capital F represents the velocity field in a fluid flow, particles near that f of xy tend to rotate about the axis, and the axis that they rotate about is the direction of the curl. So the curl is the action, it is the axis around which there tends to be a rotation. And if you think about the right-hand rule, that makes some very clear sense, because you curl your fingers this way and your finger is pointing in the direction of the curl. So particles near x, y, z in the fluid tend to rotate about the axis, then points in the direction of the curl. And the length of the curl vector is a measure of how quickly the particles move around. If the curl is equal to 0, the fluid is free from rotations at a point P, and F is called irrotational at P. So there's no whirlpool or eddy at P. So if the curl of F is equal to 0, then a tiny paddle wheel moves with the fluid but does not rotate about its axis. So the paddle wheel just moves, but it's not spinning around. If the curl does not equal to 0, the paddle wheel rotates about this axis. Now we'll talk more about this later in this course, and actually this would be enrichment material for this course, but we may actually talk about Stokes' theorem. But this is a very important thing in engineering and fluid mechanics. Now, last but not least, we're going to speak of divergence. So if capital F is a vector field on R3, and these partials all exist, then the divergence is defined as a function of three variables, and the divergence of F is equal to the sum of these three partials. Now notice that this is a scalar function, this is not a vector function. So observe that while the curl is a vector field, the divergence is a scalar field. And in terms of the gradient operator, del, the divergence could be thought of as being the dot product of del with capital F. Let's do an exercise. So if capital F is equal to this vector field, find the divergence of F. You know what to do. Let's see how you did. So you should go through the computation again. This is the dot product. So you take the derivatives and you add them together. What you should get at the conclusion of this calculation, make sure you can do this because I might very well ask you to compute the divergence of something, is z plus xz. If F is a vector field on R3, then the curl of f is also a vector field on R3. We've seen that before. So we can compute the divergence of the curl. And the divergence of the curl, this is a theorem, but the divergence of the curl is equal to 0. Now this is a simple enough proof that you should be able to prove this. Why don't you prove this as an exercise? You know what to do. Let's see how you did. So you go through and you compute these derivatives, and whenever you're computing these, because we have sufficient continuity and differentiability conditions on R and Q and P, that these things all cancel out, and this is 0. So remember that the divergence of the curl is equal to 0. Here's another example. I'm going to ask you to do this. Show that the vector field F, that is defined this way, that is x, z in the I direction, x, y, z in the j direction, and minus y squared in the k direction, cannot be written as the curl of another vector field. That is, show that capital F is not equal to the curl of G. A little bit different kind of a problem. Why don't you try to give this a go? You know what to do. Let's see how you did. Okay, previously we went through and we, in an earlier example, we computed the divergence of this, and that is z plus xz. So the divergence is not 0. Now if it were true that this capital F is the curl of some g, then the divergence of f would equal to the divergence of the curl of g, because we're putting f in there, and that would be 0. But that contradicts the fact that the divergence of f is not 0. It's a proof by contradiction. Therefore, capital F is not the curl of another vector field. Now, the reason for the name divergence can be understood again in the context of fluid flow. If capital F of xyz again is the velocity of a fluid or gas, then the divergence represents the net rate of change with respect to time of the mass of fluid flowing away from this point per unit volume. In other words, the divergence of F measures the tendency of the fluid to diverge, move away from the point x, y, z. If the divergence equals 0, then we say that F is said to be incompressible. There's another differential operator that we should mention in passing here, and this occurs when we compute the divergence of the gradient vector field. So the divergence of del F is del dot with del F, and when you do the calculation, this is what you get is the sum of the second partials. Now often people will abbreviate this del squared, because you got del dotted with del. But this is also called, it's very important in applied math, it's called the Laplacian operator, because it has a close relationship to Laplace's equation in partial differential equations. And we'll study that, well, you will study that later in your engineering life. We can apply Laplace's operator to a vector field, P in the I direction, Q in the J direction, and R in the K direction, and notice that it applies to each of the coefficients separately. You should be able to prove this. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.